recall a little bit, at this point, last time, before the midterm, we know, I need to mute phone. I need to mute my phone. Anyway. All right. So we know the standard procedure for the midterm, middle school method. Calculating GCD relies on prime factorization. So here the problem is, are we satisfied with this solution? No. To answer this question, we need to understand the prime factorization. Do you have some idea about prime factorization? How hard it is? How hard? Prime factorization.
To find all the prime numbers that multiply in order to get the number that you're considering.
Yes.
How do you do that? GCD, greatest common denominator computation.
No, GCD is not targeting prime factorization. Yeah, prime factor. This problem is very complicated one. Very complicated. Very complicated.
You can maybe apply recursion to determine the prime numbers and how many times each prime number can be multiplied to reach the.
This is not that easy. So here, let me talk about this prime factorization question, because only. All right. For prime factorization, here let's think about prime factorization for large numbers, not for small. For small numbers like this, that's easy. Okay? Yeah. So here, let's consider for huge numbers, huge integers. How huge it is? Yeah, here I'll give you some idea. Yeah. 1,000 digits. How about that? That big. 1,000 digits. One number with 1,000 digits. That huge. Okay. For the prime factorization to the right is extremely slow. Extremely slow. How slow? Be extremely slow. 1 hour to an hour, is it extremely slow? 1 hour, 2 hours? Yeah. But even much, much slower than that. Okay? Even you use supercomputer. Yeah. Supercomputers, and not just one, large number of computers connected, sharing the computation time. Okay? You can use software to spread computation time, sharing. Even you do that in months, you need to do the prime factorization, just one number factorization in months. How slow it is. Okay? Yeah. You can use the fastest possible, and there are several relatively fast, but still not fast enough. For such kind of prime factorization, extremely slow.
We're not going to go by brute force with this.
Yeah. Even advanced algorithms, there are several algorithms very, pretty advanced, based on number theory. Okay? But still extremely slow. Okay? So that causes the problem. If your GCD algorithm relies on this slow algorithm, how can you do it? Okay? So you have to drop this middle school method. If you need to find a GCD of two huge numbers, two huge integers, you need to develop some algorithm that does not rely on prime factorization. That's the point. That algorithm is available. That algorithm was available even 2,000 years ago. Euclid. Have you heard of Euclid? Yeah, Euclidean algorithm. Euclidean algorithm, very smart, very simple, and very fast. And you do not need to do prime factorization.
Very efficient for handling the major subdivision operations.
Yes, yeah, very efficient. Yeah. That's the recursion. That's the variable size reduction. Variable size. This topic of this part B. Part B. Variable size reduction. Okay. Yeah. So let's see that. All right. So then another question. Yeah. Because this prime factor is extremely slow. Yeah. Yeah. We know slow algorithm in general, it is a bad thing, right? Yeah. Because for our computer science people, we like efficient algorithms, right? Nobody likes slow algorithm, right? Yeah. But think in this way. Nobody likes slow algorithm. Can you change slow algorithm to make it benefit the society? Yeah. Make it useful. This prime factorization extremely slow. Now, we do not want to treat it as a negative thing. We make this is some property, right? Yeah, prime factorization is very slow. This is a property. Can we use this property to something good for the society, right? Something good for the society, not bad for the society. Can you think about something like this? Slow. Not just a little slow, extremely slow, super slow. How can you turn this into something very useful? People like it. People like it to be slow. How about that? Slow is a good thing, not a bad thing. Is it possible?
You have that where you start with an original number and you divide by each prime number that is less than it.
Don't get into details. Okay. Yeah. So we talk about high-level ideas. Something extremely slow, definitely it's not good for us, right? It is not good for us. But if we make this slow property, we make our enemy to face it. We don't want to face it. But we want our enemy to face it. How about that? We want to deliver this slow problem to our enemy. How about that?
It's like cyber warfare.
Yes, that's the point. Yeah.
Let's do Russia or something that.
Yes. Yeah. So here, not necessary, international. The hackers. Do we treat hackers as our enemy?
Oh yeah, everybody hates those
Yeah.
scammers. Let's screw them.
Right. Hacking, our personal information, right? Because we need to use internet to send our personal information, and a hacker try to steal our information, right? still our, very valuable information. So we want to make hacking extremely hard. How about that? We want to use this property to, if we want to hacking our encryption algorithm, then it is very hard. Okay? Yeah. So there is a famous encryption algorithm is based on this, called RSA encryption algorithm. Sorry. Yeah. 3 professors, RSA, the initial of 3 professors, RSA encryption algorithms. Yeah. The basic idea, multiply 2 large primes. Okay? Yeah. When you start, because when you do multiplication, it's very fast, right? Computer doing multiplication in less than 1 second. Even 1,000-digit primes. You can find huge primes at the beginning. Do multiplication super fast. But after that, you get a huge number, right? That huge number, if you want to decompose it, extremely slow. Extremely slow. So you use the product to encrypt your internet data, do encryption. Okay? Yeah, so that.
The product will be the number of characters that your password will.
Yeah, that kind of because when we do encryption, so if we have some code, based on that code, we can encrypt our data, right? Yeah. But that code, that huge code, extremely hard to decompose. So if the hacker even get that code, very slow to crack it. Yeah. So then, after months, years, then useless. Okay? Yeah, because we complete our tasks. So we move on, right? So, yeah. So this prime factorization thing, currently, this RSA algorithm, still the main algorithm used in internet encryption. Okay? Yeah. Yeah. But some people claim, have you heard of some new technology called quantum computing? Quantum computing, a little bit, yeah. Some people claim, so if quantum computing,
The next step up in computing.
right, extremely fast, right? People claim extremely fast. Then this algorithm may not work because quantum computing can quickly decompose the huge numbers into primes, parallel primes.
You need to update your war strategy.
Yes. That a new algorithm must be developed. Yeah. But some people claim that. Yeah. If it could happen or not, nobody knows. Yeah. Just to let you know this background. Okay? All right. But at this point, prime factorization is still extremely slow. Yeah. So still, RSA algorithm still works to protect our internet data. Okay? Yeah. All right. Then we need to calculate GCD. Yeah. So, yeah. All right. So let's get here. So we need to do the problem size reduction. Yeah. All right. So here we need to use some mathematical tool. It's called division algorithm. This mathematical tool, so simple, even grade students, they know it. Okay? Yeah. In grade school, you can do integer division, right? Yeah. Right. Right. Yeah. So here, let's write a theorem. Yeah. We write integer division as a theorem. basic theorem. Given positive integers a and b not equal to 0, because we need to use b as divisor. Divisor cannot be 0. Okay. There exists unique integer q and r. Q for quotient, r for remainder. Okay. Q and r. Yeah. So let's write integer division formula. Yeah. But the remainder must be strictly than the divisor, greater or equal to 0. Remainder. All right. Such that a equals b divisor b times quotient q, then plus remainder. Is that a simple fact? Everybody knows, right? But we use formula to write it. Integer division.
I mean, yeah, you can derive that easily. If you set q as the quotient of
Yeah.
some arbitrary division operation,
Yeah.
divide by a, divide by b.
Yeah. Yes. Yeah. But this is a fundamental theorem in numbers theory. So simple, but so fundamental in number theory. Okay? Extremely important. Yeah. Yeah. Many advanced theorems rely on this fundamental theorem. Yeah. All right? Yeah. Now we use it. Yeah. All right. This time we need to use this theorem to help us do the problem size reduction. Size reduction. Okay? Yeah. When we calculate GCD of m and n, if we calculate directly, it's hard. Then we convert it to an easier problem. Another GCD problem with smaller problem sizes. That's the basic idea. Smaller problem sizes. Yeah. All right. Yeah. Yeah. So here, let us assume m greater or equal to n greater than 0. Yeah. If n greater than n, then we swap these two numbers. Yeah. Yeah. Very easy. Yeah. To make that happen. Yeah. All right. Now, we can apply integer division, division algorithm, yeah, on m and n. Okay, yeah. So we get this formula. Yeah. With that formula, now we can do size reduction. Yeah. All right. How to do the reduction? Yeah. We do some formula transformation. Yeah. GCD. This is our goal. This is our goal. Okay. Yeah. But we have a new representation of m. Let's replace m by our new representation. Yeah. nq plus r comma n. Okay. Yeah. All right. When you look at that, yeah, there is a term nq. It's a multiple of n. Q multiple of n. Yeah. So that's something interesting. Yeah. Because the second parameter n, yeah, the first parameter contains a term that is a multiple of second parameter. This property, we can use it to reduce the problem size. Yeah. All right. Here, let me use this fraction to explain the size reduction. Yeah. If we look at the fraction m over n, yeah, replace m by nq plus r, then nq term, after we take it out, after we separate, yeah, because there are two terms, we separate. nq terms, there is a cancellation. So our quotient q, it appears as an integer. Okay? Integer q plus then a smaller fraction, r over n. Yeah. So this formula tells us some simple fact. Yeah. So we need to study this formula. The simple fact is when we consider common factor between m and n, does the q term make some impact on it. Q term, yeah. The Q term has nothing to do with the common factor, right? Yeah. Because it appears as an integer. Yeah, integer. Okay. So that tells us if we consider a common factor between m and n, we can ignore the Q term. So we only need to look at the common factor between r and n. Yeah. Yeah. Integer term does not change anything of the common factor of the later numerator, denominator in the fraction, right? Yeah. They are separated, right? Yeah. Yeah. Integer term, fraction part, they are separated. Okay? Yeah. All right? So based on that observation, can we make our conclusion? The GCD of m and n equals the GCD of r and n. That's simple. Then that's the reduction. If we can write a GCD in a different way, yeah. GCD of n and r, because n greater than r, right? Based on our assumption here, n is in the position of B. Yeah. So n greater than r. So we should swap n and r. Yeah. This is our first round problem size reduction. First round. Can we do second round? Can we do second round? The second round we need to do integer division on n with the divisor r. How about that? If r is not 0 and is not 1, what would happen if r is 0? Think about it. What would happen if r is 0? R0, this is gone, right? Yeah. And m over n is an integer. Then what is the greatest common divisor? N, right? Yeah. The divisor is the greatest. Divisor n is the greatest common divisor if r is 0. Okay? So we don't worry about the r0 case. Yeah. What would happen if r is 1? R is 1 here. R is 1. GCD is 1, right? Yeah. Yeah. So you know the answer. R is 1. GCD is 1. N and R. So GCD is 1. 1 is divisor of any integer, right? 1 is divisor of any integer. And you cannot be greater than 1, right? If it's greater than 1, then it cannot be the divisor of 1. So if R is 1, R is 0, the answer is true. You can get the answer immediately, so you don't worry about the 0, 1 case. If it's non-zero and not 1, can you do another round integer division? Divisor algorithm, another round like that. So another reduction. Keep doing this reduction. Recursion. Question?
Are you able to do just a round of this with actual numbers?
Oh, actually, yeah. We use that 64 previous number. We will do it. Yeah. Yeah, like that. Yeah, I remember. So I may have that later someplace. Otherwise, I just, do hand calculating. Yeah, okay, good point. Yeah, a little abstract, right? How to imagine. Yeah. I will do that. Yeah. So let us. Yeah. So here, this is our key formula of size reduction. Yeah. All right. So then I will show you the concrete numbers. Okay. Concrete numbers. Yeah. And keep doing this. Eventually, we will stop, right? Eventually, yeah, because you cannot do reduction forever, right? Every time your problem size is reduced, but your number is limited, right? Yeah. The integer values are limited, so you cannot do reduction forever. Yeah. So your algorithm will terminate eventually after finite number of steps. It will terminate. Okay? Then no prime factorization, right? If we do this way, you don't need to do prime factorization. You only do integer division. That's all you need to do. We know integer division very, very fast. Very, very fast. Okay? Comparing with prime factorization, extremely fast. Yeah. All right. So yeah. So you. Oh yeah. Let me see if I do here. If I do not do here, yeah. I may not do here. Okay. Then I do hand calculating here. Yeah. So you ask me to see it clearly. Yeah. Let us apply this idea to calculate our old example 24, right? Yeah. All right. To do that, all right, 60 equals 2 times 24 plus 12, right? Integer division. Yeah. Divided by 24, quotient is 2, remainder is 12. How about that? Okay, all right. There, the quotient part should be gone, right? Yeah, based on, so here, the quotient part should be gone. Yeah. So there, you only use the remainder 12. So it should be equal to GCD of, but you need to put a 24 first, then 12. How about that? How about that? Yeah? Okay? 24. All right. And 24 is multiple of 12. 24 is the multiple of 12. Then the greatest common divisor is 12. Because 12 is the divisor of 24, right? 12 is a divisor of 24. And the 12 is also a divisor of itself. And you cannot get a larger divisor than 12, right? If it's larger than 12, then it cannot be the divisor of 12. So the largest possible divisor is 12. So that's your answer. Okay? See? Yeah. Very effective. See? Very effective. Especially when your two parameters are huge numbers, 1,000 digits. 1,000 digits. You do integer division, that use supercomputer, even use our normal computer. Yeah. Basic PC, yeah, you can do extremely fast. Okay? Yeah. All right, so that's the, yeah. For implementation, this Euclid's algorithm, yeah, let's look at the basic rule. Yeah. So we summarize. This is our rule. Yeah. We summarize the rule. We have 3 cases. Yeah. When we calculate GCD, we have 3 cases. Yeah. All right. The first case, if y equals 0, yeah, it's possible second parameter y equals 0, but x not 0. Yeah. When y equals 0, x is the answer. Yeah? Because x also divisor of 0. Yeah. Any integer is a divisor of 0. Yeah. All right. But second case, yeah, here we use this percent sign, modular operation. Yeah. We know it's the modular operation. X mod y equals 0. That means x is a multiple of y. Remainder is 0. X mod y, that means we take the remainder. When we do integer division, x divided by y, we do integer division.
It's like the percentage symbol in a lot of coding.
Yes. Yeah. Almost current programming languages.
They call it
yeah.
Modulus,
right.
Modulus
Operator, right. Yeah. All right. So then, if not these 2 simple cases, because these 2 cases trivial, too simple. Yeah, we do not need to do calculation. Okay? Other than these 2, we can call base cases. These are our 2 base cases. Yeah. Then the general case. This is general case. Okay? Then we just modify two parameters of GCD. The first parameter, we use the divisor as the first parameter. Second parameter, we use the remainder as the parameter. Remainder.
Usually I've seen when I took the discrete math over the summer, and they represent X% Y, like it's X mod Y.
Yeah. If you use mod, it's also okay. But for us, percent, much shorter, right? Much simpler, much shorter.
That's why I'm always looking for like where there's a passive notation to get my points.
Yeah, fast notation.
Now what about algorithms like
Yeah.
where something always puts
Yes.
like just short differently?
Yes. Short, clear notation. Yeah, you're right. Beautiful. Yeah. All right. So that's if you write a program to calculate this function recursively following these rules, it's easy. So simple, so easy. And also extremely fast. Yeah. Okay? All right. Yeah. So here, although, remember, when we do recursion, we need to use relatively more resource. It could be slightly slow. Yeah. Here, we are willing to pay that cost. Yeah. We are willing to pay that, memory, right? Computer main memory. We need to use a little more computer main memory. But the benefit is huge because we do not need to do prime factorizations. Yeah. All right. Yeah. So here, yeah. Oh, another thing I like to mention. Here we talk about problem size, right? The size concept, data size concept, problem size, data size, data size. Yeah. M and N, it is our data. M and N is the data. Yeah. So let's review the data size. When we talk about data size concept, we may have two possibilities, right? Yeah. The first one, number of elements in the array. That's the data size. Number of elements in it. But here, it's not number of elements. Okay? Here, the second meaning is the magnitude of the data. Magnitude. Yeah. The value, how large it is. Yeah. That's the data size. Yeah. Here, we can understand the data size for this question. Data size here. We can use the maximum of M and N. Because here we have two numbers. Yeah. What magnitude you are talking about? The larger one. The magnitude of the largest, if you have several. Yeah. Sometimes you may have several parameters, right? Yeah. Then what's the magnitude you are talking about? The largest one. The magnitude of the largest number. For example, GCD. Can we calculate GCD of multiple numbers, many numbers? Yeah. For example, GCD of A, B, C, D, E, F, a sequence of numbers, right? Yeah. In that situation, what is the data size? The magnitude of the largest parameters. Largest parameter, one. Yeah, largest one. All right, yeah. So that's the data size here. All right, yeah. So we finish part B. Yeah. Then we need to go to part C. Yeah. Sorry? Yeah, here. My control is this computer, not that computer. and show and oh, yeah. All right. C here. Yeah. Part of C. Change my pen color. Oh, it doesn't work. All right. All right. Yeah. Fibonacci numbers. Yeah. So many of you may heard of it. Yeah. So let's study Fibonacci numbers.
Fibonacci recursion.
Yeah. Yes. And you know, the numbers, the rules for the numbers very simple, but we can learn a lot of things. Yeah. So a lot of, you know, important, useful knowledge we can learn from this topic. Yeah. All right. First, let me give you the question, the definition of Fibonacci numbers. Yeah. Also, the way to generate Fibonacci numbers. Yeah. All right. Through recursion, yeah. So give a recursion formula, yeah. But we need two base numbers. F0 equals 0, F1 equals 1. Yeah. Very simple base numbers. Then, our recursion formula also very simple. Yeah. So the recursion formula, F, the nth Fibonacci number, the subscript, n, capital N here, yeah, yeah, equals Fn minus 1 plus Fn minus 2. Yeah. The sum of two previous, immediate previous Fibonacci numbers. That's the generating rule. Yeah. So simple. Yeah. But the numbers generated are very interesting. Yeah. Yeah. There are many interesting properties, yeah, for the Fibonacci numbers. Yeah. All right. Yeah. Question, we need to calculate Fibonacci numbers in the fastest way. If you apply the recursion formula, it's trivial, right? Yeah. Everyone here, you can write a recursion function easily. Recursive function quickly, easily. Yeah. But the question is that the fastest way to calculate Fibonacci numbers? Yeah. If it is very slow, then your algorithm is useless. Yeah. Because for us, the most important consideration here for us is its efficiency.
So first,
How fast?
first I think the move would be to pick out a pattern, like just find the first three recursive calls, and then compute with the algorithm and patterns will start to show up.
You need to find a problem first. Yeah. 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 The yeah. So before you consider a solution, yeah, first let's try a little bit and see, yeah, because there is a brute force method, right? Can we call it brute force?
Nobody got no time for that.
Yeah. So so if we do it directly, that's the brute force. Is there any problem if you do it in a brute force way?
Like a whole whiteboard of problems.
Yeah. Yeah. We need to see the problem first. If you do not know the problem, how do you solve the problem, right? You need to know the problem first. Yeah. All right, let's see the problem. Okay? All right. Yeah. So for the first few Fibonacci numbers generated by the rule, yeah. All right. So then, yeah, let us look at the, yeah. All right. to solve this problem, actually, there are two ways we can use. Yeah, there are two ways. The first way, solve it algorithmically. Yeah, that means we use the computer science way to solve it. We develop some efficient algorithm to calculate it. Well, that's the first way. But there is a second way. Yeah, solve it mathematically. Because this equation is so simple. Can we solve it mathematically? That means, mathematically means we can find the formula for this. For any Fibonacci number, we can find a math formula for it.
That's what I was saying, the pattern.
Yeah. Oh, that's it. What do you mean, the pattern? Yeah. Right. Yeah. Good. Yeah. Derive a formula. Yeah. Yeah. Yes. Yes. Yeah. Yeah. So two ways. First, let's do the first way. Then, in our part B, we will do the second way. Okay. Part C, we do it the first way. Part B, part D, second way. All right. All right. All right. Yeah. So, the first way, let's try this is the brute force implementation. Okay? Yeah. So if we do not do anything special, let's just implement our recursive function directly. That's the brute force method, right? Yeah. Okay. This brute force. How do you feel?
I mean,
Fast or slow?
my brain is like learning the number of like basic operations it's going to take, and it's not like at the time complexity to this.
Operation, very simple. Addition. Addition, we know addition extremely fast, right?
Yeah.
Yeah.
Like when we get
Yeah.
a formula like that,
Yeah.
essentially after something's up, and we're able to solve this.
The question is, how many additions do you need to do here? If the number not under control, exploded quickly, you cannot control it. Then it's a disaster, right? That could happen.
That's what you got to develop a formula.
Yeah. Yes. Now I want to show you. Yeah, I want to show you the problem. If we use this algorithm, something really bad could happen. Yeah. How bad it is. Yeah. Let's take a look. All right. So next, I want to, first the conclusion. It's a horrible implementation, extremely slow. Okay? Super slow. But here, it's hard to imagine, right? Such a simple operation. Why super slow? Okay? Later, I will use some approach, using our algorithmic language to describe how slow it is. Yeah. Here, just say super slow.
Like with
Yeah.
time complexity and all that work.
Yeah. Time complexity. You use that way. Use big O notation. We use big O notation.
Big O, it's like big O, like n factorial, right? That's like what the efficiency of this is right now.
Yeah. Not exactly that, but pretty close. Exponential function. Yeah. The big O notation, we need to use exponential function. You know how slow it is. You have an idea. We know exponential function dominates any polynomial, right? Dominates, we know that. Exponential function dominates any polynomial. Okay? Even polynomial n to the 1/millionth power, exponential function still dominates that function. So you don't like to use that slow algorithm, right? Yeah, nobody wants to use that slow algorithm. Here, let me show you why it is so slow. Let me draw a tree, recursion tree, to show you why it is so slow. All right. Here, I use a simple example to show you. Yeah. Let's calculate Fibonacci of 6. Fibonacci, that's a small number, right? Yeah. If we use that brute force method to calculate Fibonacci of 6, let us see how many additions we need to calculate here. All right. In order to calculate fiber of 6, we need to calculate these two numbers, right? Fiber of 5, fiber of 4. Yeah. But they are unknown, right? Because fiber of 0 and fiber of 1 are given. All other fiber numbers are unknown at this point. Okay? Yeah. So we need to push these two numbers into a stack, right? Push into the stack. Yeah. I explained how to implement recursion. Yeah. All right. In order to calculate fiber of 5, we need to use these two numbers, right? Fiber of 4 and 3. But they are unknown. We need to push them to the stack, right? Yeah. Similarly, we need to know fiber of 3 and 2. Unknown, we need to push them into the stack, right? Yeah. Keep doing things like that, okay? All the levels until we reach the bottom. Yeah. The bottom means when we hit these two known numbers. These two numbers known, we can stop, okay? Then we can ready to do the calculation. But in order to calculate fiber of 6, we need to generate this whole tree. Each node in this tree, we need to push into the stack. Then to do the calculation. Think about that. Any problem?
It's like a whole lot of inefficiency stacking up.
Yeah. Any problem? Other students?
A whole lot of problems.
Yeah. So what's the biggest problem here? The biggest problem.
That tree's like got too many branches to like want to maybe cut down those branches.
The biggest. Yeah. All right. Here, let's look at the biggest part. If you look at fiber of 2, how many times fiber of 2 appears in this tree? How many times? We know there is only one number for fiber of 2. Why you need to calculate so many times? The same number in the tree, why you need to calculate so many times? You don't need it. You don't need to calculate so many times, right? One number, same number. The efficient way should be you only calculate once. That's enough, right? One number, one particular Fibonacci number. You calculate once. You know its value. Why you need to calculate second times, third time, and millions of times the same number? Why you need to do that, right? Yes. Yeah. Redundancy problem. Huge redundancy. Why this algorithm is so slow? Because there is too much redundancy in this algorithm. Yeah. So what's the solution? Now I can ask you. After you see this much huge redundancy, what is your main idea? Here we want to improve it. What is your main idea to improve this algorithm? Yeah. Can anyone tell me? Yeah. Obvious solution. What's the obvious solution here? Yeah. A lot of redundancy. What is your suggestion? Yeah. You need to give a suggestion. Gabriel? Yeah. Yeah. Use your intuition. Yeah. Something, something has a lot of redundancy. So what's your first reaction when you see it? Redundancy. We don't like redundancy. Okay? Yeah. Because it's not efficient. We want to have something extremely efficient. Yeah. The straightforward, just straightforward reaction. You do not need to do something very fancy. What is a straightforward reaction? Well, you see some redundancy, a lot of redundancy in your algorithm. Remove the redundancy, right? How to remove? You don't know. How to remove? You don't. But your goal, remove redundancy, right? Yeah. How to remove? That's our next question. How to remove? Next question. Yeah. But your goal is clear, right? We would like to remove all the redundancy. What do you mean, removing all the redundancy? Each Fibonacci number can only be calculated once exactly once. No second time. No redundant calculation. Okay? Yeah. If a Fibonacci number is calculated the first time, no second time calculation. Can you do that? Can you make this idea happen? No second time calculation. Then no redundancy. Okay? Yeah? All right. So let's do too much redundant calculation. So now for our improvement, we want to remove the redundancy. All right. Yeah. Method one. Yeah. Method one. Yeah. Method one. So here, we do not use the recursion. Yeah. Because one reason that redundancy occurs due to the recursion problem. When we do that recursion, we use stack, right? Push it into the stack. That causes a lot of redundancy. So the first thing, we get around. We do not use recursion. We get around it. So we use iterative algorithm. Okay? Yeah, that's simple. Because this recursion formula is so simple. Why we need to use recursion, right? Yeah. Yeah. We can avoid recursion. So the first algorithm, we use a for loop. This way, there is no recursion, but we can find the Fibonacci number, right? Any Fibonacci in this for loop. There is no redundancy here. Look at this implementation. No redundancy, right? Yeah. So this method, so simple, no redundancy, and very fast. So the first solution is a good solution, very good solution. Okay, all right. Now let me ask you a question. Since we have learned asymptotic notation, if I ask you, if we want to represent the efficiency of this algorithm using asymptotic notation, let me say using the big O notation. What's that? What is the big O notation of the efficiency of this algorithm? Can you see that? Big O notation. Yeah. Suppose we need to calculate f of n, little o. Yeah. Our data size is n here. What is the big O notation of this algorithm? Anyone can see it? It's not hard. Just one. We need to do one for loop. How many additions do we need? Approximately, right? Big O notation. How many additions do we need? Approximately. Not.
N minus 2.
You can ignore -2. All right? No, because when we talk about approximation, we don't need minor terms. We only keep the dominant term. So what's that big O notation? Big O of what? Big O of what? Don't minus anything. Okay? Only keep the most important term. Because we want simple representation, right? Yeah. Yeah, whatever, yeah. But the most important term is n, right? Yeah. After n, some minor terms we ignore. We don't need to worry about those little minor small terms. Yeah. All right. Yeah. Versus, remember I mentioned that the previous redundant brute force method, that's the big O of exponential function. A to the n. Is that a huge improvement? Because later you will see it's exponential function. Huge improvement. Huge improvement from exponential function to a linear function. Huge improvement. Okay, all right. Yeah. But although this algorithm is very efficient, if from the efficiency point of view, we are very satisfied. Yeah. But if we want to look at it from, some very high level general solution. Now, because this is just one problem, but we need to do things like this in many other real world problems. So from the general problem solving consideration, yeah, then this method has some limitation. Can you see that? What kind of limitation? Here we want to solve the general problems in the real world. Yeah. Not just the one relatively simple special problem. Yeah. Here, the biggest problem of this one is no recursion here, right? Yeah. We implement it without using recursion. That means we throw away the recursion here, right? When you throw away the recursion, you also throw away the power of recursion. We know recursion is very powerful, right? Remember that Tower of Hanoi. Can you throw away recursion when you solve the puzzle problem, Tower of Hanoi? You cannot. So we don't want to throw away recursion because it's so powerful. We want to keep the power of recursion. Yeah. So from that point of view, we are not satisfied with this method because it throws away the valuable recursion, that part. Yeah. So now, our ideal solution, we still want to use the recursion. We still want to enjoy the power. At the same time, we remove redundancy. How about that? At the same time, we remove the redundancy of the recursion, but we keep the power of recursion. How about that? That's the best scenario we can have, right? Yeah? All right? That's the method number 2. Yeah. All right. Method number 2, yeah. Now, there is a very important idea here. We need to develop recursive algorithm without redundant computation. That's our goal. Yeah. That's our goal. Okay? All right. Yeah. All right. Yeah. But to achieve that goal, there is a brilliant idea. Very useful in computer algorithms. There is a brilliant idea. Okay? So today I just give you some initial description because this super beautiful and valuable idea, I need to elaborate using a little more time in our next class, Thursday's class. Yeah. But today, I only have a few minutes, but I'll give you some initial description of this brilliant idea. Yeah. All right. All right. How to remove the redundancy? Very simple way so here, remember I mentioned our previous goal. So every Fibonacci number, if we calculate it the first time, we don't want to calculate the second time. Yeah. So after you calculate the first time, you should store its value. You do not throw away, okay? You do not just keep it temporarily, then the next round calculation you throw away. Yeah. Don't do that. You need to store all the calculated values. So here, the most important keyword here is the store keyword. Yeah. If you can store the intermediate Fibonacci numbers, that's not your final Fibonacci number, but you need to use some intermediate Fibonacci number. If you can store all of them, you can avoid redundancy, right? Yeah. So the main idea is just to store all the intermediate, the calculated Fibonacci numbers. for future usage. Yeah. Then you can avoid redundancy. How about this? How about this idea? So simple, right? Just use a little more resource. When you store, you need to use a little more resource, right? Yeah. We're willing to pay extra resource. Yeah. But the reward is huge because we avoid all the redundant calculation. That's the reward. Okay? Yeah. The cost, extra cost, very little. Just we use an array, an extra array to store all the calculated values. That's the extra cost. We pay, but reward. All the redundant calculation is gone. That's simple. That idea. Is it a brilliant idea? It looks simple, right? So simple, not fancy. But this idea is huge. This idea is huge. Okay? Why this idea is huge? Yeah. Okay? Because if we have that, then we can make the third bullet point happen easily. Third bullet point happen easily. Okay? Yeah. This idea is called dynamic programming idea. So that's an extremely important idea in computer algorithm, dynamic programming. Okay? Yeah. So next class I will elaborate. I will, describe this dynamic programming idea systematically. Simple, but I want to give you more description. And our project number 2, after Thursday's class, we're ready to do project number 2. We will do this dynamic programming implementation. Okay? We use this dynamic programming idea to calculate Fibonacci numbers. And then we do comparison. Okay? Brute force, dynamic programming, we compare. How much is the difference? Okay? That's our second programming project. All right, yeah, that's it. Yeah, see you Thursday. Thursday, I will give you your midterm graded papers back, part B back. Yeah. Thursday.